Thank you very much. It's my great pleasure to speak here. It's like back to home. Since 3 years ago, I stayed here. So today the topic is to give a new formulation of the gross Zagier formula. So I will not go to the proof part, but if we have time, we may discuss a little bit. I will start with the original gross Zagier formula and then move to our statement. So this. This is the first part. So let F in S2 gamma 0n a V2 new form. So it's a holomorphic cast form which is eigenform and normalized such that A1 is 1. And then we take a quadratic extension K over Q, quadratic extension. Imaginary quadratic extension. And we assume this Hegel assumption. It says every prime factor of P splits in K. P divides N, then P splits in K. And this Hegel assumption implies a decomposition of N. It's decomposed into I times I bar as ideals. Sorry, I read N OK. And with this I prime, co-prime. Now from this I, we construct elliptic curves, and then we get a point on the modular curve. Then we get a point, we call it P, which is C mod OK maps to C mod I inverse. This is a point on the modular curve, complex point. So that OK is a Z module of rank 2 embedded into C, so the quotient gives you a complex torus. And it actually gives one elliptic curve. Now we have another elliptic curve. This is an isogeny, strictly isogeny of order n because of that. So this OK mod I is just Z mod NZ. So we get a point here. And then this theory of complex multiplication says this point P is actually defined over a Lambda field. P is defined over the Hilbert class field. So we obtain one algebraic point on the modular curve. Now we try to decompose this P into eigencomponents of the modular form, and we also try to decompose it into the corresponding to the Galois group. So here we take a character. This is a character. So this Galois group is also it's isomorphic to the class group of K, since it's Hilbert class field. Now we define this P chi. We define it to be a sum twisted by chi, and then here this sigma is x on p, now minus infinity to get degree 0. This infinity is the cusp on x0n. So that gives a point on, it is not a point, it is a divisor. And then it is a point on the Jacobian. J0n denotes the Jacobian of x0n. Oh yeah, thanks. Tensor C here, C here. Now we take the eigencomponent corresponding to the Heck operators. Still in that group, that one or that one. So it's like we take eigencomponent twice. Firstly, this is like chi eigencomponent, maybe like chi inverse eigencomponent, corresponding to the action of the Galois group. Now we take eigencomponent corresponding to the action of the Heck operators. Here comes the. Yes. Tn. So now here comes the theorem. L prime f chi 1 equals So this is the formula proved by Gross and Zagier. No, that's I write here. So now I explain the notations. So this LF chi S. This is the Rankin-Selberg L function. So we may think it, so Rankin-Selberg of, we have this LFS. This is degree 2 over Q, and we have this L chi S. This actually, it has degree 1 over K, but degree 2 over over Q. We do the Rankin-Selberg, we get degree 4. And this FFPET is the Peterson inner product, and this H is the class number. And this U is the roots of unity. So it's size of half of number of roots of unity in K divided by 2 to normalize it. So it is 1 for almost all K. This dk is the discriminant. And then this narrated height. It goes from J0n, or maybe Picard, the same thing, Q bar to R. And we extend it to C as a Hermitian pairing here in their original setting. So now, here I remark the generalizations of this formula. So Shou Zhang did a lot of substantial generalizations of the formula around around 2000. Around the year 2000. So the major.
Can you remind me what's forcing the sign of the functional equation to be even?
So the Hegel condition, Hegel assumption, forces the epsilon factor to be -1. The root number, so it is odd. So actually, it's sorry. Okay, I remark here. Hegel assumption implies the root number. So 1 is the center, f chi 1, at places v equals -1. This is for v equals infinity. This is for v finite. So now the global root number is -1. So
is n squared free?
not necessarily. So in Shou Zhang's formula, this Q becomes totally real field. And this X0n was generalized to Schmer curves. Over F. And also, so now this K becomes K over F, Cm extension. This character chi becomes character of on K, more general one. Then under one assumption, it's like the conductors here should be co-prime to each other. So this F is the most important thing, becomes some pi. It's just like Hilbert modular form. And then with the assumption that the conductors are coprime. So we have conductor for this F or for this pi, have conductor for this chi, and we also have conductor of K over F, just the discriminant of K over F. Those are coprime to each other. So this is one ramification restriction. And this assumption is more general than the Hegel assumption. For example, Hegel assumption says P, if P divides the level, then P splits. So of course, this level n is coprime to, the level is coprime to the discriminant. So now recently in our joint work, in my joint work with, so the cusp was replaced by the Hodge bundle. That was also the new part of Shou-Zhang's formula. So in the joint work with Shou-Zhang and Wei-Zhang, this is going to be a book. It's almost finished. So we mainly removed this ramification assumption. So with this setting, but removes the assumption. Get the formula. Without the ramification assumption. So this L function, because of this root number assumption, it vanishes at 1. We also need that. So we, maybe in another word, if there we also have a formula even without this assumption, but then it gives 0 equals 0. It's like we.
It doesn't give you a value when
Yeah.
when the function equation's even. It doesn't give you for the value of the L function in terms of some zero-dimensional things. It doesn't that kind of gross stuff.
No. It's like 0 equals 0 by some trivial representation reason. So we had a statement very close to, very similar to this one, but just use representations. But now today, I introduce a statement using heights on abelian varieties. Abelian varieties and its duals. And we introduce automorphic representations with rational coefficients. So the new statement mainly has two things, two new ingredients. First is we compute heights of points on abelian varieties. Of course, modular abelian varieties.
You will still have weight 2 or not?
Sorry?
Is it still related to the Jacobian form of weight 2, or do you have?
Still weight 2. Still weight 2. And the second is automorphic representation with rational, or maybe say algebraic coefficients. So before going to that, we may first try to rewrite this formula as a height pairing on elliptic curves. This is straightforward, provided we have the modularity theorem. So we have this modularity theorem. This is due to Wiles, Taylor Wiles, and Breuer Conrad, Diamond, Taylor. And we also need 14th isogeny theorem to get the parametrization. So the theorem just says, in that setting, oh, no, not that setting, so sorry. The theorem says, if we have E over Q an elliptic curve over, conductor N, then there exists a finite morphism phi from x0n to E defined over Q. So this is the big theorem. With this theorem, we can move. So now every E corresponds to one F, and this P chi F really becomes a point on E. So it's easy to rewrite it. We also normalize it such that we map the cusp to 0. So then the theorem becomes L prime E chi 1. We still need this chi equals so this F suppose it corresponds to E.
So it's a particular case.
Sorry.
So this means here you would have a F with rational coefficients, not a general F.
So in this case, right?
Yeah,
The special case.
It's just in the Zagier case.
No.
The F is the phi corresponds to
F is rational coefficient, right?
No, the F and phi are, for the moment, I didn't.
way two form corresponds.
So you mean I can just write F? Phi is like an F. Yeah, we can do that.
It's related.
That's
Yeah.
you write the special case of this.
Yeah, I just rewrite it.
Not rewrite
Not
the special case.
special case of this one.
Yeah, because F cannot be, sometimes F does not correspond to elliptic curve.
Right. Special case. Oh, yes, of course, yeah. In the case that if the coefficients of F lie in Q, yeah, only in that case. Oh, I forgot that part. If F corresponds to E, and now so we should start with E, and then we find F. So sorry, we start with E. So start with E, and then we find F by the modularity theorem. And then we also have this chi, the same thing. And then we find chi and find k and chi. And then we have this statement. So now at this point, the projection to F component just becomes the map phi, map to E. So now the height now is on E. The new part is this degree phi. It comes from the projection formula of the height parent. So now we move to the next stage. We consider the the new formula we formulated. It's similar to that one, but just we use more representations. So now we first consider abelian variety. Parameterized by Schmer curves. So let F to be a totally real field. And let B be a quaternion algebra over A. So by that we mean that like B is a restricted product. Maybe it's people can't see that part. So B is a restricted product. But the key thing for us is that we do not require B to be the base change of a quaternion algebra over F.
A is a delta F, right?
Oh, thanks. So A is AF. So now this B, so we have a set sigma is a finite set of places of F. Then this B is the product pi v dv times M2 A sigma, where this dv is the unique division quaternion algebra. Over Fv within sigma. So now, if sigma, the cardinality is even, then we know we can find one quaternion algebra over F. Then this B really equals BA for some quaternion algebra B over F. But if sigma is odd, then we don't have such a thing. But actually, this is the case for our formulation of the Gross-Zagier formula for the geometry of the Schmer curves. So if this one is odd, we can't do that. Then in this case, we call this B incoherent. So in that case, we can call B to coherent. Now we assume the sigma odd, and assume sigma contains all Archimedean places. Then this B gives us a Schmer curve. Then this B cross determines a Schmer curve. X equals limit U x U. So this U is open compact subgroup of BF cross. This is like the finite part of B, and take the multiplicative group, open compact. So defined over F. And each XU is a projective curve, projective smooth curve over F. To get the connection with the classical language, the language of Schmor and Deligne, we take a uniformization, complex uniformization. So it's like for any sigma, I don't use sigma, for any tau, any embedding tau, we consider the tau point, XU tau C. Then that one has a uniformization by upper half plane. This B tau is the quaternion algebra corresponds to this sigma without tau. So we remove one place, we get a coherent one, a quaternion algebra over F. And then we get this uniformization. The cusp part is, usually it is empty. It's not empty if and only if we are in the case of modular curve. So the key property for this indicated by this writing is that this uniformization actually is true for any tau. For any tau, we just change the invariant of B to get the uniformization. So this bold B is really the intrinsic group to define the Schmerz curve. Now we make a definition. An abelian variety A over F. Sorry, a simple abelian variety is parameterized by X if there exists a non-constant map XU to A for some U, for some open compact subgroup. So this definition is analogous to this modularity parametrization. So if A is parameterized by X, then A will be automorphic. But we require a little bit more. It's like it's automorphic and we require some Zagier long length lifting to B exists.
Can you just repeat?
So remark here. A is parameterized by X if and only if. Firstly, it's like A is automorphic. And then automorphic, somehow it corresponds to this. Maybe I. Okay, you're right. Then let's go back to that later because I will introduce a lot of definitions.
Yeah.
Go back to that later, and then.
So you want A to be cut out in the Jacobian by some Ecker operators?
Yes, in some sense, yeah. For the as a quotient of the Jacobian by Heck operators.
And so it could be with multiplication by some real field, for instance.
Yes. So this is field M. It's endomorphism 0A. This is just endomorphism of A over F tensor with Q. This is a lumbar field. Finite extension of Q. And actually the degree of Q is exactly the dimension of A. So A is GL2 type by the multiplication of M.
What was the statement you made about something being a Zagier correspondence?
I will go back to that because it will be too.
Okay.
I will introduce the notations and then okay. Now we introduce one notation. This is very important for us. Define this pi A to be home C 0 x A. So this one is this one is sort of defined as this one. So this is a limit over all levels U. On each U, this is like the space of parameterizations. Now this Kc U is the Hodge bundle of the Schmerz curve, and we require this homomorphism maps the Hodge bundle to 0 on A by the push forward. So this Kc U is like a base point. It's just like we normalize like that. Now infinity is replaced by Kc. Since if the Schmerz curve is compact, we don't have infinity. So Kc U is the Hodge bundle on Xu, and in the definition as a base point. Map Kc U to 0 on A up to the torsion, since we tensor with Q. So this is just the set of all parameterizations, and then it has an action by the Heck operators, Heck correspondences, and we take the limit, so it has action by the whole multiplicator group, B cross. So we let this be infinity cross act trivially. And it also has an action by M. So the action of mx here, and the Heck operators x here, and so we get multiplication here. And then those two actions commute. So we change the viewpoint a little bit. We get this pi a is a representation of B cross over an M vector space. So this is what we mean by automorphic representations over number fields. So the coefficient now is M. M is not C. It's a number field. So now for any embedding iota from M to C, we use this embedding, then we base change, we get a complex representation. Then that one is close to the automorphic representations we usually talk about. Pi a iota this one is a complex representation of B cross. Oh, I let the infinity part X trivially. And then that's sigma A. So this B cross is not an algebraic group over F. So to talk about the automorphy of this representation, we mean the automorphy of its Zagier long length correspondence. So this sigma A iota, this is defined to be the Zagier long length of pi A, Zagier long length lifting of pi A iota. So this can be defined locally. Sorry? Now this one is automorphic.
So you're just pointing out that the Zagier long length correspondence can be defined locally.
Yes. Yes, so this pi A, sorry, this is irreducible admissible. And then it is a local product, and locally we define it, and then we get a tensor product.
Right, but then
It's a theorem.
it's a theorem then that
It's a theorem.
Zagier gives you an automorphic.
Oh, yeah, yeah. Yeah, this is a theorem, but this
I'm just trying to.
this is a theorem, yes.
This is your theorem.
Not really. That sort of follows from the, but I don't say anything. I just define that one, and now I will say it is automorphic. Okay.
It is a theorem.
Yeah, this is essentially Eichler-Schmür. Then it is automorphic. Now I say that automorphic, this capital, discrete way 2, everything we want. Weight 2, 2, 2. That part follows from Eichler-Schmür.
So the reason you
And
say
Zagier
Zagier
length.
is that you're defining this object locally. Is that the reason you said that? The local description of Zagier length. Is that what you mean?
Yes.
I'm a little confused with the central character. Will it be trivial or?
Not necessarily. The central character of pi a, not necessarily.
Finite.
Yeah, it's finite. So it depends on m. If m is totally real, then the central character is trivial. It's real. It's still still could be quadratic. So now here is a result. This is a theorem, but it's not that hard. This is proved by us, but it's straightforward by this construction. That's sigma a iota. This is a set. This one actually descends to a sigma a. And irreducible, admissible representation of sigma a of this GL2A. Sorry, not exactly correct. I can only take the finite part. Take finite part. Finite part. Over m. Maybe I don't write finite here. It's just too annoying. So I take finite parts here. Then here we take finite part. And then this is like an orbit. All base changes are here. Now actually we get one representation over m. Then this sigma a is like the Zagier length lifting of this pi a over m.
I remain a little confused. If you have weight 2 to 2, does it mean imply that the central character is the absolute value?
This, yes, the central character is finite.
Not absolute value.
Even the whole central character is finite. Has finite image. So I mean, yes, at infinity, what you can imply is it is just unitary, but we can have more.
Because the accumulative, the pi infinity is has a trivial central character.
That's how you view the spatial representation.
Yeah, because you see, start with the b, this incoherent b. The b infinity acts trivially. So Zagier length has a trivial central character.
Not absolute value. I'm always confused with some square root of cube occur in some R field in the L function.
So this one has a trivial central character is triggered at Kindle place. So non-Kindle place, just like gamma 1 n. So this one, if you sigma modular curve, you have gamma 1 n instead of gamma 0 n. So abelian varieties as a part of Jacobian of x1 of n. For x1 of n, central character may not necessarily trivial. The trivial become x0 of n.
So it's like, yeah. So now I can finish this remark. So this A, let's say over F, simple abelian variety. Then A is parameterized by X. F still it's still not so clear here. Sorry, this I want to write more. I just write here. It's like that. If this L as A, the L function is a product of this iota, and then L as minus a half, this sigma A iota.
Local.
This is global, no problem. Global is not enough?
No.
We put finite part here.
Yeah, no, it's not enough. Each place. Because you need a determinate representation.
Okay. So for each V, for each V does not divide infinity, and with this set sigma A iota, each one is automorphic. Automorphic capital way to everything. And the Zagier Langlands lifting exists. Maybe of course. So I should go quickly. So now we consider this L function. Now we can define this L as pi A as a formal Dirichlet series. With coefficients in M. So this pi A will be decomposed as a local inner tensor product, and for each one we can define a local factor. Coefficients are in M. So this is only a formal series since it's in M, not in C. But then once we pick one embedding, we'll get a complex Dirichlet series. We can talk about holomorphic continuation functional equation. So now we view it as a function from C to this M tensor with Q, C. So for each embedding, we get one function. Vector value. Now we consider our quadratic extension. So now let K over F to be a CM extension. So this is like next stage. This is like the Zagier formula. The new formulation. CM extension, then we take a point P, fix one point P in X E cross KAB. This is like this is K cross fixed part of X. It has two copies of the Schmer variety associated to K. This is just a same point. And then suppose we have a character chi from A cross, from the Galois group. With L, where L over M is a finite extension. So our pi A has algebraic coefficients. So now we want our chi also has algebraic coefficients. Now we pick a finite extension of M.
What's E?
Oh, I keep the, sorry, thanks.
Maybe change the K to E, then K equals E.
K equals E. But so originally E is an elliptic curve. So now suppose we have this F in pi A. So this pi A is home, cos X to A. So by this F, we map this point to A. Then get a point. We call it P chi F, defined to be integration so that lives in A F bar Q tensor M M L tensor with M Galois invariant. So this is the same point, the eigencomponents. Then we have the formula. Finally, we come to the formula. Assume the central character agrees with chi. So by that we need to view chi as a, so this is view chi as a character of A E cross by the reciprocity law. So this pi A is the representation we constructed. Then for any F1 in pi A, F2 in pi A dual, we have this P chi F. So this identity is in, this is important. It's vector valued, it's in L tensor Q over C. Sorry? Eta is at K over Q. K over F. So it's like we take embeddings. For every embedding of L in C, we get one identity. We basically need to C, then we can talk about those L functions analytic continuation. And then those are defined in C. Those are in C.
Glad to see you move to the point of half. Well done.
Yes.
Is that because you use the unitary correspondence now instead of the reasonable one?
This number?
Yes.
It's just a different normalization.
Irrational.
Yeah, but because we use the
Please,
language of automorphic.
what's the alpha there? What's alpha?
Yeah, alpha is the local factor. So this alpha, where alpha is defined as a local product. Of course, this is if F1 and F2 are decomposable, then we have that. And then this local one is the same as the local factor in Watts-Paget's formula. Our proof is actually inspired by his formula. Eta is still just eta. Pi AV. F1, F2, yeah. Yeah, so, but I first remark that, so we need a parent on the local representations. Oh, that's another story. So we have a parent, that's pi A cross pi A dual. We have a duality. Dual here can be actually moved to here by the duality. This duality is defined to be F1, F2, maps to volume of XU. I don't say volume, just degree of the Hodge bundle. And then F1, F2, U. So this is like this. If we have F1, it gives XU to A, if this is F1U. And if we have X2U, F2U, now we take the dual of F2U. So to take the dual, we need to first consider the Jacobian. This one factors through the Jacobian. We already take the base point as a Hodge bundle. So now then F2 dual. So now it's like, so we have, we want to A to JU. This is F2 dual, F2U dual. And then to A. This is F1U. Now we take the composition. We get a map from A to A. And by definition, this is an element of M. And this is just a normalizing factor between different levels. By this normalization, it does not depend on U. Then this is a duality map.
U is any open compact subgroup, so those XU will be geometrically disconnected curves.
It's
Yes.
connected over F.
Yeah, over F is connected, but geometrically it's not connected.
What is this degree of canonical bundle?
So the degree of the Hodge bundle.
Yes.
So, okay. Degree of CU. There are like two interpretations. One way, the lazy way is like we use the dx dy 2 pi y squared on this x u c. So we have a lot of components. We use this one to integrate. And another way is like it is almost a canonical bundle, and then you modify by those ramified points, mainly the cusps and the elliptic points. So now this pi a, this is a parent induces, so locally, abstractly, we have this equivalent parent, pi a to m. So this is a local parent. Local duality parent. By the global duality, we know those local group representations are also dual to each other. And now we normalize the local parent such that the product gives the global one. So this is the global one. Oh, I use brackets, but here I use, sorry. This is tensor. And one more thing is, this integration only makes sense after we base change to C. But then once we base change to C, and then actually we can see that the number we get actually lies in L. Then that part, this number, this local root number, local number, this term lies in L. Actually lies in L. Not just L tensor Q tensor C. You first compute it in that, and then you can prove it's in L. But this part lies in C. C tensor 1. The C part, this part. And that part is vector valued. It needs both parts. That part lies in L. So the last thing is the narrated height. So the height is also vector valued. So we have this height, narrated height, from A f cross Q times A f cross Q to R. And we have action of M, and also action of M here, a dual. So now it factors through the tensor. Sorry, it's almost finished. So mx here, and you can move here by the dual action. So here, not yet. And then that one factors through a map to R tensor M, not R Q M, and then that part is the trace map. So this map is not M linear because we even don't have an action of M on that one. Now what we do is there's a unique factorization such that we take values here and then take trace of that part to get R. Then that part is M linear. And then now the height is also takes values in here. We replace R by C. So, okay, I should mention one thing. This one equals 1 for almost all. Otherwise, it doesn't make sense. This one, alpha V, equals 1 for almost all V. For almost all V. I'll stop here.